Okay, so just now we introduced, we can record to the process, the enthalpy change of the process to determine which substance are better to use to melt ice. So we can say these two substances are better to melt ice. But in fact, the sodium chloride, we also using the sodium chloride in the winter, to try to stop the ice. So do you know why? So in winter, we also use the sodium chloride in this substance to stop the ice, to stop the formation of ice on the road. We also, like on the road in the winter, on the road, we also put some sodium chloride on the road. So using this way, we can stop the formation of ice on the road. Why?
Oh, it's me now?
Yeah.
It's because this one kind of like it does it absorbs heat. So when it's on the road, there's no way of ice actually staying on the road because initially it's hot. And that's Lush, look, he said those
Okay, I just want to tell you the answer. The answer is when the sodium, when a little sodium chloride dissolved in water, so the melting point of ice or water or the melting point of ice will decrease. What does this mean? We know for the water, the freeze point is 0 degree, right? For water. So if some water on the road in the cold in the winter, so when the temperature is 0 degree, okay, some ice on the road, right? But if we put some sodium chloride on the road, so the sodium chloride will dissolve in the water, right? So now the water is not pure water; it's a sodium chloride solution, and the freezing point of sodium chloride solution will be lower than 0. Will be like -1 of some, for example, -1. So this means when the temperature is 0 degree, the water will not change to ice. Okay, so this is why we can still put some sodium chloride on the road, and then make the freezing point low. How much it can be low? You can check on Google. I'm not sure. Maybe now the freezing point of water changed to -1, -2. Okay, so when the temperature is 0 degree, still no ice. So this is why we can still use this sodium chloride to protect to stop the formation of the ice. But we also can use this into the ice or on the road because when it dissolved in water, it can release heat. So this is about two different concepts. Okay.
So let's say here talking about it being lower, so meaning zero degrees it won't freeze. But if it is, for instance, 10 degrees, or rather that kind of means like it's initially what is hotter than 0 degrees, right? I mean, if water boils if water freezes at 0 degrees, if what's on the road is 10 degrees, meaning there's no way water can freeze until like passing that 10 degrees, right?
Of course, if 10 degree, not if the water cannot be.
That's what I was trying to say. So I was like, if on the road there is NaCl, which is, for instance, that's what I thought. I thought maybe it's like higher because you said the top ones, those two, the ones that are negative, they give away energy, like they release energy, right?
Yeah, but this energy can, when, the question, the key point is when temperature becomes 0, ice or not. Before 0 degree, like 10 degree, it doesn't matter heat, release heat or obtain heat, because it will disappear, right? Just we just thinking about it. When temperature is 0 degree, now ice or not, we hope no ice. So if it's 10, more than 10, like 10, of course it can absorb, but it doesn't matter for to what we think about. We care.
So what I was saying was kind of correct. What I was saying, like the answer I gave, looking at the different angle I looked at the question.
Yeah, this is different. It's the same question, but different using this different theory to explain. Different theories,
Out of point.
I was right. But I was right.
Yeah.
On the road, if you, let's say you have 2 roads, the other one puts sodium chloride, then the other one puts calcium dichloride. So which one will be more effective?
The question is which one is more effective?
Effective.
If it is this one and this one,
Calcium.
Yeah,
this one and this one,
sodium chloride.
this one and this one.
Yes.
Which one?
Sodium.
They expand using different theory. So maybe I don't know. I didn't. You can do an experiment.
It depends to the situation.
Because this is different. One is about melting the ice. This is used to melt the ice, but this is used to stop the formation of the ice.
Good.
So I don't know how to do it. Which one
What do you want to do?
which one's better? Which one is better? You can see this both way.
He's making us what's his helpless.
I think like when the ice is formed, when the ice is formed, it's better to use this tool.
To make it work.
Yeah, but before the formation of ice,
You don't want
this is the work. But of course, before the formation of ice, this also works. They also works because they also form the solution. Okay, they also can lower the freezing point. But why we use this? Because this is cheap. So the chloride is very cheap. So we just put off the road, But this, this I think is best. Yeah, this is definitely cheap, right? So the chloride is you can find it in many places. So it's cheap. This is why we use this put on the road to stop the freezing of the formation of ice. Okay, but if when the ice is formed, we can use this to help to melt the ice. Okay. Yeah, this process this picture to show these two process, 2 steps of the formation of solution. The sodium chloride. Okay, the first is like a crystal structure, right? So solid structure, and the step 1, it should absorb this energy to form this kind of states. Okay. And then they will be surrounded by water. For example, this is sodium. Okay, the sodium. No, this is chloride. Chloride. The big one is chloride. So the chloride is close by the water. Okay, the chloride has the negative charge. So this is hydrogen. Okay, the hydrogen has plus charge. So the hydrogen will tend to close to the chloride. And this is sodium. The sodium, the oxygen will close to the sodium. So when the formation of this kind of states, this process will release energy. So here absorb 788, but this release 784. So this means it is still absorb 4 kg more energy. So this is why. But this sum is very, very small, right? It's not. This is small, but this process still need energy from the environment. But for some other substance, maybe this energy is lower than this energy. So after the formation of solution, the system will release energy. So in this process, it need energy. It will absorb energy. Okay. So this is why we can reasonably claim this guy has a minus charge, this guy has plus charge, just because the energy difference of these two steps are different for them. Okay? And all this level, all this energy can be measured from experiments. Okay? And yeah, this is a very common table, right? You can find this on the food. And this, like apple can, if we eat the apple, can give you this energy, okay? And gasoline, the gasoline is much higher than other substance. Okay, so this is why we can use this to the car. Okay? Yeah, beer. Okay, beer. So this level is the energy. Okay. What? Anyway. Okay. Yeah. Homework. Okay, this is about this chapter. And the homework is like using this deformation of the enthalpy of the substance to calculate the enthalpy change in the reactant. Okay. No? No, not this time. We still have like we still have three more weeks, right? 3 more weeks. So we still have three chapters. So we need, and this chapter is long one. And also this chapter, I think this is the most difficult chapter for this course. So we need more time to. What?
Let's not talk about logic.
Yeah.
So are we having a review?
Review now. Just so for semester basically 16 weeks for class. So just 16 weeks. Now this week is I think it's 13. Yeah, 13. Yeah, 13 weeks. 13 weeks. So we still have 3 weeks. So after 3 weeks finish. And so basically before we have a final exam. But the problem is some students are not here. So we can't so in the before just final exam for 2 hours, and then you must stay there, but it's open book. Oh, now you don't have book. Okay. You can still say your homeworks, because some like the final exam, the question is the final exam will be similar to your homework. Now some students are not here, so we just give you a text, so you finish it after 1 week, like homework.
Oh,
okay.
So that's
Yeah, and of course I hope you can't copy each other, otherwise you will. Yeah, don't let others know your answers, okay? And also the text is like 30%, okay? And your total score is depends on your text and homework. And the attendance, of course, attendance is no problem each time, everyone comes, okay? Yeah. And yeah, so in the 17th week, I will give you the text.
So,
That's question.
and for monitor also.
Uh,
Max for monitor.
ma-
Max for monitor.
He wants free marks this one because it's the
For
money.
monitor.
for more.
Maybe 2 points. It's maybe 2 points.
Anyway, okay. So we will discuss more about the later. Okay. So now this is about the chapter 14. Yeah, this is more complicated than other chapters. Okay. So then also we need to spend more time for this chapter. So I can't finish it today. You know.
Yeah.
Okay.
Good.
So this is about the spontaneous change. We will introduce the entropy and free energy. So in this chapter, we will introduce what is entropy, and we will introduce the third law of thermodynamics and the second law of thermodynamics. So in the last chapter, we introduced the first law, right?
Yes.
First law of the thermodynamics. So in this chapter, we will the third and the second. So the first one is about the entropy. So what is entropy? So before introducing entropy, we need to know the spontaneous change. What is the spontaneous change? So a spontaneous change is one that occurs without external intervention and has definite direction. This example, for example, the ice. This is ice. This is liquid water. If the temperature of surrounding is more than 0 degree, the ice will change to water, right? And if water put in the environment with the temperature lower than 0 degree, the water will change to ice. So the ice in this condition, the ice can change to water, and in this condition, the water can be changed to ice. So this process is called spontaneous change. Because we don't need to do any other thing, we just put this in the environment with the temperature more than 0. So this process will happen, resolve. So this is called spontaneous change. Spontaneous change. Okay? So the change is in enthalpy during a reaction is an important fact in determining whether a reaction is favored in forward or reverse direction. So what does this mean? Because the change in enthalpy it also means the change of energy, right? So this enthalpy change is an important factor to determine the reaction, the reactions. For example, if an exothermic reaction more likely to be spontaneous than endothermic reaction? Not necessarily. The endothermic dissolution of amino nitrate occurs spontaneously. Okay, we think about for the first step. Of course, enthalpy change is very important. For example, if the reaction from left to right, for this reaction, it releases energy. If this reaction from left to right, release energy. So basically, this reaction is easy or not to happen. It releases energy. Is it easy or not? Easy, of course. Because it releases energy, of course. This means the products have low energy. The reactants have high energy. And of course, the substance with high energy is easy to transfer to the substance with low energy, right? Like we put somewhere in this position, energy is high, right? And it will fall down, right? So basically, if from left to right, if we release energy, of course, this process, this reaction is spontaneous. Is spontaneous. But some like endothermic process is also spontaneous. This means, for example, for some reaction or some process, it needs energy. It needs energy, but it still can happen itself. So releasing energy is not the must condition of this spontaneous process. Okay. But of course, if the process releases energy, it is spontaneous. But sometimes if it absorbs energy, it still can be spontaneous. Why? Why some reaction, some process absorb energy, but they can still be spontaneous. So this means both endothermic and exothermic reactions can be spontaneous. There are additional factors which determine spontaneity. So basically, first is energy. Second, important, matter tend to become more disordered. So energy is just one very important factor. Another important factor is matter tend to become more disordered. This is why for some reaction, although it needs energy, it still can be spontaneous, because this process becomes after this process, the system becomes more disordered. If the systems become more disordered, this is also easy to happen. So this a measure of disorder is entropy. So this is entropy. Now here we introduced what is entropy. Entropy means a measure of a disorder is entropy. Okay, now what is disorder? Okay, here we use an example to introduce the entropy. So there are two paths, right? And A, B, and in B there are some gases. The gases is yellow, okay? And here is a vacuum, nothing. And here is closed. If here is closed, all gases will be in this side. When we open this valve, we will open here. So some gases will go from B to A, right? For example, A here vacuum is 0 atom. This is 1 atom. If we open here, so half gases will go from B to A. So each one has 0.5 atom. So of course, from this state to this state is a spontaneous, right? It will happen by itself. You don't need to do any other thing. But this process can go back to this. For example, all the gases will come back to here again. It's possible or not? It's impossible. Impossible. Because when it will just stay like this, it can't go back. So all gases will go back to here? No. Right? It is impossible. So this is from this state to this state is possible. But in this stage, all A come back to B is not stable. So this process is not spontaneous. It's not permanent. And of course, if you can use some other forces to make these gases, from A to B back to B. But spontaneous means you don't give up external forces. Okay, so all gases back to B is not possible. So this back process is not spontaneous. Not spontaneous. Okay. So now we introduce what is disorder like. A, for example, if in this case, in this example, there are many gases atoms, right? We can simplify this process. If only two molecules in this side, in B, okay? If we open here, so there are 4 possible, right? There are 4 possible. So first, if over here, so there one can be the green, the blue one, the red one. Okay, the blue one can be this side, red one this side, red one, blue one, and also, of course, this is possible. Both of them go back to here, right? Because it's only 2. Because they are moving, right? They always move the molecule. So it's possible. This back to here, right? Or both molecules back to here, go to this side. So from here we can see that when the valve is open, there are 4 possible arrangements or states for both particles. So, and also these arrangements are all equal in energy. This means they also, the possibility for each one is the same, right? It's the same. So, opening the valve allows a higher degree of disorder. In this, there's only one arrangement. And here, there are 1 changing to 4 arrangements. So this means this is more disorder. This is more disorder. So the reversion process of 2 gases particles occupying only one flux is not spontaneous.
So let's see.
There says not these arrangements are equal in energy. So what about quantity? Are they also equal?
Equal means the possible of each one occurs is the same. The possibility of each one of each state to occur at therefore this means they're all strained, right? But the possibility of each one for a long time is the same. For example, okay, if we can say there are 4 minutes, okay, total for this state 4 minutes. So each one will have 1 minute, right?
Yes.
Each one has 1 minute. You can't say, oh, this one has 2 minutes. This one has 2 minutes. Oh, this one has only 1 minute. This one has only 1 minute. No, right? If it's 4 minutes, so this one will be occurs for 1 minute. This one occurs for 1 minute. This one occurs for 1 minute. So this means they have the same energy. Their probability, their possibility to occur is the same. So this is they have the equal in energy. If one has high energy, it means this guy occurs more times. But for these 4 arrangements, they are same. They are equal, right?
With the same volume.
What?
Or have the same volume.
Yeah, of course. Yeah. Your question, Monica?
Or yours.
Okay, good. Yeah, good question.
Thank you.
Okay. So now we know the disorder. In this case, the disorder it has more disorder. So this example is like this. For example, in a crystal structure, in a solid crystal structure, the atoms can move, right? In crystal structure, we know each atom just stay at the crystal point, right?
Yeah.
They can move. So it's like this state. Okay. But in solution, they can move, right?
Yeah.
So in this solution, it's like this. So this means for a substance, there are atoms in the crystal structure has fewer arrangements, right, than that in solution. Because in solution, it's like this. They can move. They can move, it means they have more arrangements. But in the solid state, they have few, they can't move. They have few arrangements. So the substance in solution has more disorder than in solid, right?
Yeah.
Okay. So this is about the disorder. And of course, if the substance has more disorder, this means it has more entropy. It has more entropy. So it can become more disorder. More disorder, it means more entropy. So an example is a substance in solid state has fewer disorder than in solution. So this means the substance in solid state has fewer entropy volume than in solution. Okay? Now you understand what is entropy, what is disorder, right? And the disorder also decides the process is spontaneous or not. Okay? Okay. Yeah.
So that statement you give so does it also apply to say the substance that liquid state also has less what?
Gases.
Yeah,
Yes.
compared to gas.
Of course. Yeah, good. Yeah, the substance in liquid state has fewer disorder or fewer entropy than in gases. Yeah, good. Nice. Okay, now we'll introduce. Okay, so here we can say from this state to this state is spontaneous, right? But from this state to this state is not spontaneous. Why? From this to this is spontaneous, but from this to this is not spontaneous. Why? Question. Your turn. Why? now how to explain this process? Now we introduce the disorder, right? The disorder and the entropy, and also spontaneous or not. So why from left to right is spontaneous? From right to left is not spontaneous.
When we open the valve, it
Yeah.
has a higher degree of distortion.
Good. Yes. It is high disorder. Yeah. So it's high disorder. So this means it is spontaneous. Because spontaneous is excited by two facts. One is energy, another is disorder. If the process release energy, it's spontaneous. Or it becomes more disorder, it's spontaneous. So from this to this is not, because from right to is disorder decrease. And no energy change, right? No energy change. But the disorder decrease or the entropy decrease, so it is not spontaneous. Yeah, open the valve allows a higher degree of disorder. The reverse process of to get the product occur only one place is not spontaneous. Okay, now we know this process, how to determine the process is spontaneous or not by energy and disorder. Okay, if we give more molecules, like 4, okay, so for 4 molecules, and each one, we can name like 1, 2, 3, 4, right? Because each one is different. Each one, so they are like a total 16 arrangements for these 4 molecules. So as the number of particles increases in systems, the number of possible arrangements that the system can be increased. And the process in which the disorder of the system increases tend to occur spontaneously. Like from A to B. So from A, if we stop, if it's closed, just only one stage. But if we open here, if we open the valve, so it can have 16 arrangements, and its disorder increase. So from A to B is spontaneous. Okay, so here we can see ice melts spontaneously at when temperature is more than 0, even though it is an endothermic process. The reason is it absorbs heat, but its disorder increase. So this process can also be spontaneous. We know, so in the molecules of water that makes the ice crystal lactic are held rigidly in place. So the disorder is very low. But when they melt in the water, so they are more free to move around. So and hence more disorder than in the solid state. So the melting increases the disorder of the system. So this process is also can be spontaneous because its disorder increases. Okay, so that's all today, and we will continue this chapter next week.